So we are talking about capacitors, and I want to give you guys some theoretical backing for that. Remember, I should just write this. And remember that we've already done the Millikan oil drop experiment. So we essentially had two capacitor plates. We had a plate at the top. We had a plate at the bottom. Plate at the top could have a plus or minus 500 volts, or it could have 0 volts. Plate at the bottom was just grounded. So it essentially was at 0 volts. So we have what is known as a potential difference. And with this potential difference, we can cause charges to move up or down inside of an electric field. So what do we have here? If this is positive, then electrons should flow out. So that means our electric field will go like so. In other words, we're saying that we have a bunch of positive electrons up here, if it's a positive voltage. Okay, so we have ourselves an electric field in between these two capacitor plates. And then, we put oil inside of this and we watch charges rise or fall. So we had ourselves a charge here. And basically, if this oil droplet had a negative charge, then that means that it would rise under the influence of a force that was described by Q, and that's the charge on the particle here, times E, and that's the electric field as a result of the voltage that we're placing on this thing. So the particle would rise, and of course there's a force that's going to act downward, two of them, and one of them is the gravitational force, and so that's just going to be mg. Let me just erase that. I'll just put E here. Then we had a gravitational force, mg. All of these are vectors. And we also had a resistive force that was acting to oppose the motion of this particle, and we just described that as K, V, R. So all of that is not super important right now, but I just wanted to connect it to this because we're not looking at moving charges in a capacitor. We're looking at the energy that's stored inside of a capacitor, okay? And what are we getting to? We're saying that as long as we can cause a separation of charges in a sense in a capacitor, or if we can store charges at the top of a capacitor plate, I can just have pluses here, which means it's the absence of electrons, and then we have an excess of electrons over here, which, either one of them could hold, where we don't necessarily have an absence, we just have an excess of electrons down at the bottom. So any two can work. In other words, we can have an absence of electrons at the top, or we can have an excess of electrons, or we can have both. Okay, so to create a capacitor, and that is just going to work without charges again moving inside of it, like the oil drop experiment. So with that, let's go into the geometry. Voila, the geometry is right here. And instead of doing this, let's just duplicate, or not duplicate, but let's create a new page. And so let's say we have two plates. Like so. I would much rather them be circular. Like so. And in between those two plates, we have a substance. We have a dielectric constant, or we have an insulator. And this insulator it basically has a dielectric constant associated with it. We call it kappa. And so we have an area of overlap to represent part of the capacitor. And when I say area of overlap, I'm talking about how this particular, and let me pull up some color here, how this plate overlaps with this plate. Okay. Just in case that wasn't clear, how this plate on this side overlaps with this plate. And the material in between is some insulator that we're choosing. It could be rubber, it could be air. Air is an insulator. Okay. The other thing that we want to consider is the distance of separation between the two plates. And the distance of separation looks like this, D. All right. So we have ourselves a perfect example with Millikan's oil drop experiment. We just turn it on its side. We apply voltage to one side of the plate, plus on this side, and maybe a minus on this side. And we know that the electric field is just going to go from one side to the other. Okay. And so once we have this, this is just the Millikan oil drop experiment turned on its side. And this is our representation for a capacitor. And when I say representation, it's the geometrical representation. And there's a formula that we can use, and that is C is capacitance equals to kappa, which is the dielectric constant, times the area of overlap over the distance of separation. So C is capacitance. Kappa is the dielectric constant. A is the area of overlap. I'll just write this up here. Overlap. And D is the separation, the distance of separation between the two plates. So plate separation. So we've formally specified everything in the capacitor. Okay. In the next video, we want to use this in connection. We want to symbolically represent this particular device, and it's going to look similar to this. This is how our capacitor will look symbolically. So we're going to use that to get a little bit deeper into our representation for capacitance.